Okay, so in the previous lesson, we talked about goodness of fit. Essentially, does our observed distribution match does our expected, do the observed and the expected match up together? I don't know why that was so hard to spit out, but alas it was. And we were looking at one single categorical variable in one single population. Now, today we're going to move on to our next type of chi-square procedure, which is a chi-square test for homogeneity. Now, in the name, homogeneous tends to mean of the same being, of the same belonging. So here, the homogeneity of proportions test is used if a single categorical variable is measured in two or more populations. Typically, the variable will be listed horizontally, and each population will occupy one row, usually giving us a two-way table for our data. Now, no expected distributions are provided for this type of procedure, so we're going to use a new formula for the expected counts, again, in the long run. And this is because I don't expect certain populations to vary one way or another, but I'm measuring how this one categorical variable varies among the different populations. So this is going to be very similar to our test that we're going to learn in the next lesson, which is a chi-square test for independence, but there's just a subtle difference. Here we're looking at a single categorical variable in two or more populations, homogeneity through the different groups. Now, the null hypothesis changes from the earlier lesson's goodness of fit. And here, we believe there is no difference in the distributions of a categorical variable across the populations or the treatments. However, we might have evidence that suggests that there is a difference in the distributions of a categorical variable across the populations or treatments. So initially, I assume there's no difference. It doesn't matter what the population is, but I'm trying to prove the alternative here, which would suggest actually there is some type of difference based on which population group they're in. Again, alpha is 0.05 unless otherwise specified, and our assumptions do not change. We still want a random sample, typically a simple random sample observational study, or a stratified sample, because again, we're looking at the different categories in these various populations, or a randomized experiment. They are independent if our sample size is no more than 10% of the population. And again, this 10% condition only needs to be checked when doing random sampling without replacement. If you're doing a random experiment, then of course your results will be independent of one another since they are receiving different treatments. And then lastly, our large counts condition that at least 80% of all the expected counts in the data must be at least 5. And we have to show the work. We can't just say they are met. We have to show what these values amount to. Now, if these conditions are met, we will use a chi-square test for homogeneity. Again, the indicator here is that there's usually two or more populations, and we're looking at one single variable. Now, we have this new formula here, and think back to Unit 4 when we were looking at probability. If two events were independent, we were able to just multiply both events. So in the same way, this formula is derived from the same idea or concept. So we're going to take the row total, and we're going to take the column total. We're going to multiply those two bad boys and then divide by the total sample size to give what we call the contribution to the tested, or sorry, not the contribution, but the expected count. So this is, again, in the long run average, if I kept sampling over and over again from these two populations, this is the value that I'd expect to get in the long run. Now, in order to find the contribution to the test statistic, each of those expected counts, I'm going to take the difference between the observed count and the expected count, square that to emphasize the difference, and divide it by the expectation. And that will give me the contribution. And eventually, if I summed up these contributions, I would obtain the full-on test statistic here for the chi-square. Now, we have a new way to calculate the degrees of freedom. Here, it's going to be the number of rows minus 1 times the number of columns minus 1. So instead of the number of categories minus 1, we have this new handy-dandy formula. The chi-square formula is provided on your AP Stats formula sheet, but not the degrees of freedom formulas. Same thing, since we're still measuring a difference that's as large or more extreme than the one that we're observing, we're going to use a greater than probability. And same decisions here. We're going to compare our p-value to our alpha or significance level, and then based on that, we're going to give a conclusion in terms of the alternative hypotheses. Now, do Republicans, Democrats, and Independents think alike about the primary system in the U.S.? Each group was asked if all primaries should be held in June of presidential election years. 718 Republicans were asked, 734 Democrats were asked, and 76 Independents were asked. The results are shown below. So Republicans who thought it was a good idea, 266, Democrats 308, Independents 28, etc. This is the first opinion, is the good idea. Then we have the poor idea, and then we have the no opinion group. So all of these are the observed counts. We actually took our sample, and this in the sample, these were the total counts for Republicans with who thought it was a good idea, Independents who thought it was a poor idea, Democrats with no opinion, etc. Now, since this is a two-way table, I can actually use marginal distributions to help me out here. So I add up the total number of Republicans, regardless of their opinion, and there's 718 Republicans, as stated. Same thing for Democrats and Independents. Now, ignoring the populations from which they're sampled, I look at how many people thought it was a good idea, 602. How many thought it was a poor idea, 543, and how many had no opinion, 383. So this gives me a total sample size of 1,528 politicians. Now, is there significant evidence to claim that these different groups think alike on the issue? So here, I'm going to use my null, which is that there's no difference in the opinions across the parties. Regardless of whichever party you're in, everyone thinks the same on this opinion. However, we all know that's not true. So my alternative hypothesis here is that there is a difference in the opinions on this issue across the parties. Now, you can see I kind of cheated here, but I started my expected matrix. And the way I get these values is I take 602 times 718 and divide that by 1528 to get approximately 282.9. I do the same thing for 543 times 718, divide that by 1528 to give me 255.2. We take 383 times 718, divide that by 1528, get about 180. Now, I'm committing a statistical sin here because this isn't the official expected counts. This is just rounding error due to human fallacy, human variability. Now, these are not the true long-run expectations. In the calculator, it gives you the more precise one. And, of course, we always want to be as accurate as possible, but for the sake of notes and examples, and even on the AP exam, they're gonna relatively accept this rounding idea. But when in doubt, don't round, just copy what you get from the calculator or your calculations. Now, so I have my expected counts here, and it's already going to help me see that one of my conditions, which is that they're all greater than 5. So let's check the rest of our conditions here. The first one is that I've obtained random samples of 718 Republicans, 734 Democrats, and 76 Independents. So my random condition is satisfied. Next up, since I am sampling without replacement, I'm not going to ask somebody about their affiliation and then put them back in the population. Instead, I'm going to note that I've already asked them. So I can assume that 718 Republicans is less than or equal to 10% of all Republicans. I can assume that there's at least 7,340 Democrats in the population, or that 734 Democrats is less than or equal to 10% of all Democrats. And the same idea flows here for the independents, that 19 independents is less than or equal to 10% of all independents out in the population. Random's been met, independent has been met. We look and our expected counts are all greater than or equal to 5. And since all of our conditions are met, we use now what is called a chi-square test for homogeneity. And the way I recognize this is because I'm looking at the categorical variable, and then I'm looking at how it varies throughout the different populations. So I'm looking at, do all of the populations follow this idea that they all have the same ideology between good idea, poor idea, and no opinion? Or based on the population, is there evidence to suggest otherwise? So since I'm going to use a chi-square test for homogeneity, I'm just going to repeat my procedures as following. I'm going to take the chi-square, I'm going to find the statistic by summing up the differences squared of the observations and the expectations and dividing those by the expectations. So I take my Republicans here of 266, I subtract it by what I expect, I square that and then divide by the expectation, and I do this until my last category, which was the independents with no opinion. And if I were to sum up these 9 cell counts, I would obtain a test statistic of 4.017. Now, my p-value is going to be the probability that my chi-square statistic that is greater than 4.017, assuming degrees of freedom 4. And the reason I found degrees of freedom 4 is because I had 3 rows, 3 minus 1 is 2. 3 columns, 3 minus 1 is 2. 2 times 2 gives me 4 degrees of freedom. I obtain a p-value of 0.4037. So just some things to highlight here is that each of these sections, each of these fractions, this is what we call a contribution to the test statistic. The actual test statistic is the total summation of these contributions, but each little cell here, those differences, are what we call the contribution to the test statistic. And then next up, degrees of freedom. This has changed from our goodness of fit test because now I'm looking at a two-way table. And lastly, we obtained our p-value here, which is greater than any reasonable significance level. Thus, we fail to reject the null hypothesis. Again, here, we don't have enough evidence to claim that there actually is a difference in opinions on this issue across the various political groups. Maybe, again, our sample was just wonky, or we fluked out, or maybe we made a mistake. But as of now, where we stand, there's no significant evidence to suggest that there is a difference. Instead, we don't have enough evidence to disprove that there's no difference. A lot of vocabulary going on there, or verbiage, but essentially, we don't have enough evidence to convict. We just have enough evidence to say there's not enough evidence to claim otherwise. Okay, so let's go back to our probability days and look at this next example here. And a company claims that the dominant color of the shirts that students wear differs between male and female students. So notice I'm looking at two populations now, but I'm also looking at the shirt color preference. Now, a random sample of 120 female students is selected, and another random sample of 120 male students are selected, and the following results are for their dominant shirt color. And I'm given this two-way table. So go ahead and pause the video and attempt to find these test statistic contributions and probabilities. Okay, now hopefully you had a good blast from the past looking at some of these probability questions, but let's go through the answers here. Contributions for the test statistic for males who prefer blue shirts. Well, 76 males prefer, 120 males are sampled, and 76 people prefer blue, and divided by 240 gives me an expectation of 38. The difference between the observed, which was 49, and the expected value, which was 38, 11 squared over 38, gives me a chi-square contribution of 3.1842. Now the same logic follows for females who prefer other shirts. Again, notice I took the row total of 120, multiplied it by the column total of 54, and divided by my total sample size of 240. And I get 27 here, and again, I just do observed minus expected squared divided by expected to get my contribution. Next up, I look for males who prefer other shirts, and I notice that same thing, 120 and 54, so the expected count should actually be the same for the males. So I just borrow that over. Again, observed minus expected squared divided by expected, and I notice that my test statistic contribution is the same for both males and females who prefer other shirts. I look here for the test statistic for females who prefer black shirts, and here actually our expected count meets our observed count, so we have a test contribution of 0, so this isn't going to alter. There's actually no difference here. What we expected is actually what occurred. Next up, to find the degrees of freedom, I take the row total minus 1. Here I had the males and females in my row, so that's 2 minus 1. And then I look at the shirt color categories of black, white, blue, and other. That's 4, and take 1 away, that should give me 3. So 1 times 3 gives me 3 degrees of freedoms for the situation. And then lastly, are the events of being a female and preferring a black shirt independent? I calculate the probability of being a female. 120 out of 240 of our participants were female, so that is a 50% chance. Then I calculate the probability of being a female given that you prefer the color black. And back to conditional probability days, we look at the intersection divided by the condition. So 36 out of 240 over 72 out of 240 gives me 36 over 72, or also 1/2, which means the events being a female and preferring a black shirt are independent since the conditional probability does not change from the total probability. Regardless of the condition, it hasn't changed, thus it is independent. So that's just a little bit more practice with our chi-square test of homogeneity. So the next lesson we're going to talk about is now our final chi-square procedure of independence. So good luck.